Good afternoon, everyone. For those of you that don't know me, my name is Dave Eckroat. I'm the director for IDEA US, and we are doing our March webinar. So this one is going to be to discuss simplifying steel to concrete connections. While we're going to be focusing a lot of the time on base plate design, it is also, IDEA can be used to design kind of embed plates, beam connections to concrete walls, those types of things. So we will have an example of that going forward. So next slide. So again, just kind of the general, if you've listened to one of our webinars before, you can see that there's a question panel right in the main panel of GoToWebinar. Feel free to ask questions there. And then we will respond, and there'll be some Q&A afterwards. Just to let everyone know that's attending, we're trying something new this time. So GoToWebinar actually has a certificate, basically an attendance certificate that unfortunately is not super customizable, but that will be included in the email that you receive after the webinar. So I know a lot, that's been a question that we've had quite a bit as far as for continuing ed. So this way it will be sent to you automatically. So that's one thing we're trying to work on. So next slide. So just to go over the agenda today, really going to be jumping into the software quite a bit and talking about some different types of connections. So biaxial base plates with the shear lug, kind of showing you a corner base plate with some stiffeners and double wideners, discussing weld plus contact, and then kind of showing you how multi-grid operations, and then kind of looking at some of the other operations within the software, general cross-section, how to do imported DXF for a plate design, the concrete block offsets, like I said, contact and weld, as well as bolt and anchor grids, and then we'll also do some Q&A. But before we get started here, just going to do a quick poll question. So this one's a pretty simple one. Just asking you, how would you categorize your firm regarding connection design? Do you do full connection design, maybe only some complex ones, maybe it's only base plate design, or you just completely delegate all the connection design? So we're going to leave this open for about a minute here, and then I'll close it. Give it another 10 seconds or so. Okay, I'm going to go ahead and close the poll, and let me just share the results. So interestingly, and not actually super surprisingly, the majority of you design all your connections. Also good to kind of see the distribution. So thank you for doing that. And what I will do is I'm going to be handing off to Johan, who's one of our product engineers here in the US, and he's going to run the rest of the show. So Johan.
Alrighty, thank you, Dave. So for today's webinar, we're basically going to be covering a few of the best manufacturing operations or features that can be used for steel to concrete connections. And before we start the first demo, we'll run through the features and then show you that demo where we can apply these features or manufacturing operations. Now, typically when creating steel to concrete connections, there's different ways to model the transfer of shear forces. As you can see on the bottom right corner, we have 4 different types. So the first one, friction, we basically have the shear resistance equal the friction coefficient multiplied by the compressive load. For the anchors, the shear resistance is determined by the shear resistance of anchors. For sliding, this is typically mainly for member application, and it's when we're trying to work with sliding supports. But for this purpose of this webinar, we are focusing on the shear lug for this demo. And in the shear lug, it is simulated as a stub or part of a member, and it is encased in the concrete under the base plate. Now, the really good thing about the shear lug option is that whenever you choose this option, you have the full freedom of the cross-section navigator, meaning that you can input any typical cross-section, but aside from that, you can also use the general steel cross-section. Now, with the general steel cross-section, it allows you to create custom creations of shear lugs made out of built-up cross-section shapes, and it also helps you improve the efficiency in your modeling. Now, this is not only that we'll cover on the first demo, we'll also cover the DXF plate import. So basically, the DXF plate import is a very good feature that allows you to import your own plate geometry. So let's say you have a very complex geometry that is otherwise not possible within the plate editor. You can typically just draw these 2D geometry in your CAD file, export it as a DXF file, and from there, we can import that DXF file into Idea Statica. So this is a process within the stiffening operation. And so this manufacturing operation basically gives you full access to the plate capabilities, one of them being the DXF import. Now, for the first connection that we are covering will be the biaxial base plate with a cruciform shear lug. Now, this connection basically will show you the previous two features and manufacturing operations that we covered into this connection and show you how you can benefit from this design. So now if we basically just jump into Idea Statica, once we open it, we are directed to the main window. We'll click on connection, and this is where we use the connection application to start our model. All right, so once we open this connection, we are taken to the design tab, and this is where we can start editing our connection. So first thing we will want to do is adjust our column cross sections. So all you have to do is click on it. On the right-hand side, we have the data. So here we'll choose a new cross section shape, open our cross section navigator and choose a rectangular HSS. So here it's a matter of just choosing the correct dimensions, and automatically you are taken to the search box so that you don't have to waste time. Here you are shown filter material libraries that you can choose from. If you scroll to the right, you can click on that star, and on the left-hand side, these are saved as your favorites. So for ours, we are choosing the correct thickness, press OK, and we already have the right material property. Once we click OK, it automatically gets updated, and the next thing to do is adjust those bracing members. Now, although these bracing members are HSS, we need rectangular, circular HSS, so we'll have to add a new cross-sectional shape. So here, again, it's a matter of just searching for the right cross-section dimensions, choosing the right library or going to your favorites, and then the correct thickness. Now, for the member M3, there's really no need to create a new cross-section because it's already created. All we have to do is click on the drop-down menu and click the previously defined cross-section. Now, after we do this, the next thing that we want to do is adjust these angles. So for both members, I'll just adjust them to 52 degrees. And next thing that we can do is start adjusting this base plate. So part of the base plate template is that this base plate was already edited. It already has a cut with it, and this was already made within the plate editor. To access this and reset it, we can go to the editor, right click on it, or go to the operation and click editor. So here, all we have to do is come to the operations. These are the operations that we have available for plates. In this case, we don't need additional operations. What we are trying to do is place it back to its original shape. So to do that, we right click and delete and click apply. Now we have the original shape of this base plate, and now we can start editing its dimensions. So first thing for the material, let's go ahead and change this. Again, just plus icon, and it's the same process for the cross sections. We'll just select the correct material property and its thickness. I'll adjust this to 3/4. Now here for the dimensions, there are different types of dimensions that you can choose from. For our case, we'll choose profile. On the next demo, we'll cover this more in depth. Now here is where you can start adding the dimensions for your base plate. So whenever you choose to profile, you are able to choose the 4 different offset edges for the offsets of the profile, which the profile is the member. So if we turn to transparent view, here you're able to see the offsets a lot better with the dimensions. So here for the top, we have a 1-inch offset for member, the member column. So here at the end of the member, we're offsetting that plate 1 inch. So that's basically where the offsets are coming from for the top, left, bottom, and right. For the purpose of our connection, these are the given offsets that we're creating. And for the coordinate and orientation, we'll just leave it as is. Now for the anchors, instead of using this regular A325 material property, we can click the plus icon and we have different material libraries as well as sizes. So once choosing the correct one, you'll just click OK. In case these sections are not found or these sizes are not found within the library, you can always create these as well. Now I'll just adjust this to 20 inches and I'll remove the washer plates. All right, now here for the anchors, instead of figuring out what all these are, let's just go ahead and set them all to 0 and go to the top window, top view. Here we can also again turn on to transparent view to see our anchors a lot better, and we can start dimensioning these. Now you do see that we have these additional anchors. We don't need them, so one way to locate where they're coming from is just click on that given component. It redirects you to that operation. So because we only need the base plate operation, we don't need this grid operation, so we'll just go ahead and delete it. Here we return back to the base plate. Our dimensioning becomes a lot more clear and we can start adding our position of the anchors. This position of the anchors also relates back to the coordinate system and the dimensioning that you set for this operation. So these dimensionings are also offsets based on the profile of the column. So here we'll offset 2 inches all around so that we can get a symmetrical positioning for the members along the profile of the member. Now here we just turn to solid view. Next thing to do is adjust these welds. 5/16 and 5/16 for flanges and web. Now here is where we'll start looking at the added features within IDEA. So here for the foundation, we'll just finish by editing the offset, adding the depth. Now for the shear force transfer, instead of anchors, we'll select shear lug. Now shear lug, by default, you're giving an I-beam for the shear lug, but in case you have your own custom design, this is where you can start doing it. So instead, just click the plus icon to access the cross-section navigator. Instead of using the rolled cross-sections, which are predefined cross-sectional shapes, we can always go to the welded compose, click on the general steel cross-section, and within here, we are taken to the plate editor where we can add our different shapes. So in here, we'll select the general plate. Here is going to be one of 2 plates that I will be adding to add my cruciform. So with this type of plate selection, you can edit the thickness and the length so that it can be easier for you to create your shape. So here I will just do 12 inches with 1/2 inch thickness. Select the correct material property and click OK. So here in this window, you'll start seeing all the different cross-sectional shapes that you are going to be adding to create your built-up connection. So here we can always copy or add a new plate. Here I'll just add a new one so that I can re-specify the length. I will still keep it at 1/2 inch, but instead of 12, I will do 8 inches. and I will click OK. So now the way you align or make sure that these plates are connected are by dealing with the master components. So you have to kind of reference these plates along with each other so that they can be read as one. For the first plate, you don't really need to reference anything because that's the first plate. So for the second one, that's when you need to start referencing the plate. Here for the master component, we'll choose the first plate. The master point is the point where you will be using from the master component. So every master component and the other components will have their own insert points. If I want to keep it at the center line, I will keep both at 0, and all I have to worry about is the rotation. Now, once I do rotation, we also have translation offsets that we can do to customize our share log a lot more. Since we're satisfied with this design, all we have to do is click OK and just exit out of our cross-section navigator. With this, our share log will be created already, and then we will be given more parameters to edit it. So here for the length, I will do 6 inches, and for the rotation, I will rotate it 90 degrees. So with this, I already have my share log created for the base plate, and then I can move on now to creating the connection for those bracing members. Now here we don't really need these added operations. These gusset plates will not be something that we will use because we have customized stiffening plates. So here, in order to add these stiffening plates that are customized that will not otherwise be available within the plate editor, we can use the stiffening plate operation. So here within the stiffening plate operation, for the shape, aside from regular or circular, you can use the polygon option. With the polygon option, this is where you will see the DXF option. All you have to do is click on it. You will be redirected to select the file that you have created for your plate. You'll just open it, and a new window will be shown where you can outline this geometry and import it into Idea Statica. Now, one important thing to do before you start outlining and importing into Idea is to select the correct units. If we select inches, start the numbers, and start outlining our geometry, you will be able to import it correctly. Now notice that I only clicked it once and the whole outline was created. That's because on the original CAD file, it was created as a polyline, but you can always use different lines and then select it manually. And this is where the number feature will come into place. Now, once we have the consecutive line, we can just outline it, and on the right, it will give us the dimension for that new geometry. If we click OK, that plate will be imported into our model, and all we have to do is just adjust its dimensions. So here I will do some offsets so that I can create the plate at the correct location. So here I already have this new edited gusset plate so that it can connect my member M2. Now, following this, I will show you just how to do different methods on how you can use this gusset plate to connect to the bracing members. The first one we'll review will be through the gusset plate operation combined with this complex stiffening plate. So first, what we need to do is go to the operations and click on a cut-off plate. The reason we're doing a cut-off plate is because we want to cut the stiffening plate by the column so that it is welded at that location. We do have two different types of cuts. We have cut-off member and cut-off plate. Cut-off member, as it states, it will only be able to use for the entirety of the member. But for a cut-off plate, you can use this to cut plates or plates of a member. Since we're cutting the stiffening plate 1, we'll go ahead and use cut-off plate. By default, the correct members are already chosen. All we have to do is just adjust the weld. So here for 3/8, we'll just do 1/4 inch. And the next thing that we need to do is add a cut so that we can add a weld here between the stiffening plate and the base plate. You might be inclined to add a new operation, but you can always right-click and copy that same operation. all you have to do is just redefine your members or plates. We're still working with stiffening plate 1, but instead of cutting it by a member, we're going to cut it by a plate. As you can see here, you can use base plate 1, and then we'll just add 5/16 thickness. All right, so now that we have this, the next thing that we can do is create the connection between the gusset plate and the member M. To do this, the first option that we'll cover will be through this operation, the gusset plate operation. Now, it is important to know that the gusset plate operation will only work with these existing plates if they have already been cut by a member. In this case, since this plate is already cut by the member, we will be able to use this feature. So let's go ahead and start adjusting these parameters. For the gusset plate, the member that we're connecting, instead of being the column, we're connecting member M2. Instead of creating a new plate, drop down menu and click on the existing plate. Here, the existing plate is the only one that we have, which is SP1. And then we can jump onto the connection. Now, you might think that this connection is already connected correctly, but if we go to the transparent view, if we observe around it, there's really no yellow lines representing the welds between the bracing member and the plate. And if we further observe, the shell elements are continuous along the path of the plate, so there's still no cut being made. And this is where the connection option comes into play. Now, so here we'll start adding the gap, and this gap has to do with the gap between the bracing element and the end of the column. So this is where we're getting that 1.5 inch. And to add that cut, we'll start notching the member. By notching the member, we're able to create that cut and add that weld around it. We go to solid view, we now have this weld along the member. We'll just need to adjust this weld to 1/4 inch, and we can move on to the second member. Now, to add the other plate that is also customized, we don't need to create a new one or bring in the DXF. We can take advantage of copying these connections and just realign them. So for this one, all we have to do is just change the offset from the X, add it to the Y, and change our directions for the plates. So as you can see here, the stiffening plate gives you full liberty, not only of bringing the DXF, but where you want to locate your plate. All right, so now this plate will be different from the first plate that we created. Instead of being cut by the member column will be cut by the stiffening plate, meaning that the plate will run through continuous along the column. So to start this, we'll first create a cut because we need to cut the member by the plate. So if we go to operation, this is where we'll use the other operation, cut of member. And here we're specifying we're cutting the column by a plate. So instead of a member, we'll choose a plate. Instead of the base plate 1, we'll choose our second stiffening plate. Now you will see a warning message for this cut, and that is because we're using bounding box. Whenever we're typically working with HSS or cuts that are not going to be continuous across a cross-sectional shape, we'll choose surface. The surface will create the cut around that cut path so that you can just create those cuts along there. Now here we'll just fix these welds, adjust them to 1/4 inch for both. Now, one thing to mention for HSS, the welds, when we define them, they're always defined by webs. So removing these welds for the flanges has really no effect on the welds that are being displayed. Before we move on, you might be inclined to choose a double-sided fillet weld for this connection, but a double-sided fillet weld basically creates a fillet weld along the selected member on both sides. So instead of using a double-sided fillet weld, we'll just choose the front side fillet welds. So they can only be on the outside and not on the inside. All right. So now, last thing that we need to do for this plate will be to add another cut of plate. So we can either go to the operations or right click and copy. Here, what we need to do is just specify the second stiffening plate, and we're already referencing the base plate 1. Now here, instead of selecting one-sided, we'll select two-sided, and we already have that weld. Now, after this, next thing that we can do is connect the bracing member onto the plate. And this is where that gusset plate operations will not be available. So instead of doing that, we can work with the working plane. So if we go to the operations and choose a working plane, the working plane is usually and mainly used for bracing members, and that's just because it gives you an easier access to position your members. So if we go to transparent view, for working plane under the origin, we can always choose to reference a member for the origin. By doing this, we are able to obtain the local coordinate system of that given member. So for a bracing member, this becomes a huge advantage just because you have these members at an angle, so you don't have to worry about manually positioning them with your X, Y, and Z. So here, since we now have the local coordinate system of member M3, I can just specify the offset from the working point. And just a way to verify, wireframe view, this is the working point where we're referencing the starting point. Now with this, what we can use the working plane with is with a cut. So here we'll introduce a cut of member. So this cut basically will be cutting the new bracing member M3. And now instead of using a member or a plate, now we can also use a working plane. With this, now we have created the cut, the first initial cut that we need for that member in order to create that offset. Now this offset could also be created within the member options, but we don't really recommend this because whenever you do these offsets, you also change the force position. So instead of kind of messing with the force position, you can resort to these operations so that you can create those offsets without moving this force position. Now we'll need another cut for this so that now we can cut bracing member M3 onto the stiffening plate. So here we'll look at member M3. Now instead of the working plane, we'll select back again to a plate and select our second stiffening plate. Here basically we already have this connection, and both of these steps give you the same results. Now this all depends on the different types of plates that you have, as explained earlier, and we also cover the shear load. So there's kind of ways that you can take advantage of different operations, combine them, copy them, so you can efficiently create these models. Now, if we go back to our next demonstration, before we move on, what we'll cover on the corner base plate will be mainly the concrete block offset. So now with the concrete block offset, this feature is found within the base plate operation, all the way at the bottom with the offsets. Now with the offsets, typically you will only input one value. When you input one value, this offset is symmetrical for all four edges. But we also offer two additional options in which you can input these offsets. So the first one, as mentioned, we have the uniform offset. The second one, we have left to top, which meaning you only input two values. So for the first value, the left and right will be the same. The second value, the top and bottom, will be the same. Now, if you want to fully customize your offsets to take into consideration instances where you have maybe a corner plate, could be attached to a base plate or a wall, this is the option that you might want to go with, where you can specify the offsets for all four edges, starting with left, right, top, and bottom. Now, this is where we'll jump into our next demo, which is the corner base plate. So now, again, for the corner base plate, we'll start by going to our connection model, creating a new template. Now from this template is where we'll start again with another base plate. And if we go back to our PowerPoint, what we're looking at is a white flange connected to some stiffeners and to the concrete. So here we can start with a white flange, maybe sort of start with this template that already has stiffeners, and we can create the connection. From here, these templates typically bring us more efficiency because we don't have to specify so many parameters. All we have to do is things such as adjusting our cross sections. So here, instead of a 12 by 79, I'm going to choose a 12 by 87. Now with this 12 by 87, I can then just adjust the material properties. Since it is a white flange, all I do is plus icon and have the material library. Double click for OK. And here's where we can start editing this base plate operation. Now for this base plate operation, to start with, we'll have to fix this material for the base plate. Instead of A500, let's choose a stronger steel, so maybe A572 grade 50. Now here I'll just adjust this thickness, and this is where we have the different dimensions. So here we have to profile symmetrically. Basically, the top and left will have symmetry for the left and right and top and bottom. Which is rectangular, we can define our offsets based on the working point, and circle will be the same thing. So in our case, if we were to choose rectangle, we go to top view. Instead of specifying your base plates based on the profile of your member, you can specify the actual dimensions of the base plate. One of the advantages is that you have full control of the dimensions of your base plate, and you can have better values on your detailed drawings. So basically, instead of doing offsets where you might not know the full dimension of that base plate, this will be the other way to do it. So here we'll just do 12 inches on all 4 sides. And another good thing that we can cover here will be the coordinate system. So here, as you can see, the coordinate system is at the member and the orientation is perpendicular. So right now we have a base plate to the concrete, but let's say we had the column at an angle. Rather than 90 degrees, we had it at 45 degrees. Because on the base plate, we have it set to the orientation perpendicular, it will always be perpendicular. But if you still wanted to model it as horizontal, you can also do that. Now, if you wanted to model also a wall, you can also do a vertical orientation for this concrete block. For our block, we'll keep it at perpendicular and go back to our column and adjust it to 90 degrees. Now, if we move on to this base plate features, we'll just, again, change the type of anchors. We already have this because on the previous connection, we had already defined it. So the anchoring length, I will just adjust this to 16 inches, and I will add a washer plate. Once we add a washer plate, you can see it on the bottom being made, and we can also adjust the size of it. Now here for this stiffening plate or base plate, we are going to add some anchors. And the way we are going to add the anchors is basically, ideally, we want to position them around this column. But because the anchors are set by patterns, we will not be able to do this manually. So if I start creating our patterns for -9 inches and then 2 more bolts spaced at 9 inches, -9 inches and then 9 at 2, I will have my first row of 3 bolts. Then if I add again another left layer, I can do -9 inches and then another one 9 inches at 2. So I want to have a 3x3 but exclude the middle bolt. Now from here, I did not mention that for the coordinate system, you can also change it from the member. So these are also not offsets from the member. And this is where we'll choose global. So for the global, we are actually dimensioning them from the working point. Now, as you can see here now that we are in the transparent view, we do have that middle anchor bolt that we don't need in our model. So you will not be able to take this bolt out of it with these top and left layers options. The way to do it is go to the plate editor. So within the plate editor, you are able to see all your different bolts and the position of them. As it is right now, you are not able to do anything with them, but if you click explode, you can always select that anchor that you don't need and delete it. We'll just click apply, click OK, and now that anchor is not longer in the solid view or in the analysis. And now what you will see here is now that these positioning for the top and left layer are grayed out because that original pattern is no longer available. Now, if you did wanted to adjust this, you would have to go back to the plate editor, restore this bolt configuration, and then you will be able to adjust it. So here, I'll just go ahead and fix the flanges and the web wells. And this is where we will go with the concrete offsets. So for the concrete offsets, this is where you will start. So basically, since we are at the global coordinate system, we will be able to start with left, right, top, and bottom all the time. So here, if I start with the left for 10 inches, right 2 inches, top 2 inches, and bottom 2 inches, I will create sort of a corner plate model. I'll just go ahead and adjust this. And one thing to show is that if we were to change this coordinate system to member, these dimensions are adjusted. So if in any instance, the rotation of this member were to change, also the dimensions of these offsets change. And that is because we are referencing the member and not the global coordinate system. So these are one of the things that you can always take into consideration when adding these offsets, not just for your base plate, but for your concrete block. All right, so now that we have these things, one thing that we can quickly do is add some stiffeners. We do have the widener operation, but these only work for the plate ends. Now, if we wanted to add multiple plates, not at the plate ends, we can always take advantage of the rib operation. Typically, users might be inclined to introduce all these stiffeners as different stiffening plates and create cuts and weld them separately, but we also have the rib operation. So with the rib operation, you're able to select what members and plates you're connecting them to. All we have to do is again adjust this material and then select the right cross section. Instead of selecting the web, I want to choose the bottom flange. Now, another way for you to know which plate you're selecting correctly is by coming over to the solid view model, hovering over these plates, and on the bottom left corner, you will see information here for the material properties, the cross section, and the thickness. So now that we've confirmed it is the bottom flange, we can then adjust these parameters. For transparent view, both on surface gives you 2 stiffeners, but in this case, we only want the stiffener on the outside. And now we can just adjust the position of the stiffener. So here for the X position, I don't want it interfering with the anchor, so I will move it 3 inches. And now, instead of adding a new rib operation for the other stiffness, I can just change that repeat count to 2. And that delta will be the spacing from the previous stiffener position. So it was already at -3. So if I want it equally spaced on the other side, I will do 6 inches. And this is confirmed on the transparent view. We are already spaced equally. Now, if you did wanted to add these stiffeners on the other side, all you have to do is just copy these operations. For the shape, instead of triangular, we also have rectangular, but we can also do chamfered stiffeners that you can add to your models. Now, to add them to the other side, it's as easy as right-click, right-click, and then copy these plates. All we have to do is basically just redefine the cross-section part. Instead of working with the bottom flange on the second rib, we'll work with the top flange, and then we'll just have to adjust the surface. Originally, we had it at the lower, but we can always change it to the other side to be on the upper side. Now, if you did want it to add the stiffeners at the plate ends, that's when you can also always use the widener operation. This operation is always going to be on the left-hand side of that rib operation on the very first row. So we click on the widener, as you see, you will be able to add it on the plate ends. So here you can always specify whether you want it on all parts, just the flanges, or the webs. In this case, I don't need it at the webs because these stiffeners will be interfering with the anchor, so I will only specify the flanges. Specifying the flanges gives me only the 4 stiffeners, and I can move on with my model. So here, basically, we had a total of 8 stiffeners, and we only needed a total of 3 operations to create our stiffeners into the base plate. So now this is a really good way for you to be able to introduce stiffeners onto your connections without having to do them manually. Also how to edit your concrete blocks to be able to have different scenarios within your modeling. And this is basically covering the corner plate operation. Now from this, we can go back to our presentation and move on to the other features. So now the next one that we will cover will be contact plus weld operation. This is a really good feature, but it's also something that should not be used as an everyday operation. The reason being is because when designing critical base plates that need to transfer loads from the column to the foundation, there will be times where you can reduce these costs by enhancing the fabrication. So typically, this is where you can add a contact feature along with the welded operation. Whenever you do create a weld between the column onto the base plate, only the weld constraint is created between these two. So all that compression is taken onto just by the weld. Now, one way that you can help these weld checks is by adding that contact. But before that, you need to specify with your fabricator or your shop that you do want the connection between the column and the base plate to have no gaps. So basically, precisely machining that column end or milling that column end precisely so that there are no gaps. When doing this additional contact operation, the model will have a higher stiffness, and during the analysis, whenever the weld starts yielding, the contact will be activated and the compression will be taken by the contact. So this is one way that you will be able to lower your weld checks. Now, one way to differentiate this from your checks will be here at the bottom. The weld symbol will have a downward arrow to represent that additional contact restraint on your model. Now, again, this is something that should not be used as in everyday cases, but it is handy to know that you have access to this additional contact feature added to your weld. Now we'll just move on to a quick model to show you how basically you could start from a model, not passing your welds, and then adding that additional contact operation. So now if we start with our kind of modeled connection already, typically, if we go to the transparent view, once you create your base plate, you will be creating a weld and a cut operation to connect the column to the base plate. So under the transparent view, typically you'll see it as only a yellow line for representing the welds. If we run this calculation, basically all that compression that we're inputting into this column will be taken by the resistance of the weld. So as you can see here, as part of our results, we have a traffic light. Basically anything you see here on gray, it's 0 to 60% utilization. Green is the optimized region, orange is the warning, and red is basically what's failing. So here we can also confirm that our welds are failing because they're being overloaded. Now, if we go to the transparent view and turn on our contact operation, which is from the weld, and we can easily access it here through the operation and adding a weld operation. So here with the weld operation, By default, you have a weld, but you can always change to contact. So here, the first plate will be referencing the edges. The second plate, we're referencing the surface of that plate. So the edges that we're referencing are coming from the column, and the surface is coming from the base plate. Once that contact is created, you will have a mixture of red lines and that yellow line. Red lines are the contacts. The yellow lines are basically the contacts. So now here is where you can confirm that you have both weld and contact. So now if we start running our analysis for our connection, this is basically a finished result. And as you can see here, our weld check has gone tremendously down to 76% utilization check. And that is because possibly once that weld started yielding, our contact started kicking in and took on the added compression. So now if we quickly move on to our last part of the demo, which is the bolt anchor grid operation. This is basically an operation that gives you freedom to connect anything to the concrete, basically. So you have an independent anchorage, and you will be able to reference any plate or member to connect. So as you can see on the right, we can reference stiffening members, stiffening plates, part of the members so that they can be connected to the concrete. With this, you're also able to combine multiple operations into one model so that you can be able to get different bolting patterns or different connections. Now, if we start with our connection, let's go back to our model and create a new connection. Now, with this connection, what we are going to do is pick a beam. We'll start with a column again. Start with a simple shear connection. We'll click create. Now, instead of for this last one designing a base plate, we'll start with a shear connection to the concrete. And the way to do it is basically you can start, instead of having a vertical position member, we can always change its pitch to 0 degrees. From here, all we have to do is again adjust our cross sections. For my model, I am choosing 18 by 55. The 18 by 55 with the correct material library. Choosing material properties, and I have that now. Now here within the base plate operation, I'm going to use this partially, but not for completely connecting my member. So here I'll quickly add the correct material properties. So A36, and then thickness of 1 inch of 3/4. Here I'll just add some offsets. So here I'll do 4 inches and I'll do 2 inches from the member perpendicular. I'll go ahead and choose the correct anchor. So I'll use grade 15, grade 55, 7/8. Now here, instead of welding that beam to my wall and to the base plate and to the wall, I'm going to choose no weld. The reason is because I'm going to be connecting these through the cleat operation. I'm just going to use the base plate as the starting point for my connecting point for my steel to concrete, but I will not use it directly for the connection. So here for my anchors, let me go ahead and adjust them. So I will do 13/16 and 13/16. Once I have that done and I don't have a direct connection with them and I can confirm with the transparent view, I can go to the operations and insert a cleat operation. With the cleat operation, I will be able to connect this cleat from the column onto the base plate. So here, what I'm referencing is the column web 1, and then I'm referencing the base plate. So here I'll go to a plate, base plate, and then I'll choose my correct cross section. So here I'm looking for a 4x4, choose the correct material library, and I'll use 3/8. So here I'll just go ahead and choose this one, click OK. And now I can start setting up this connection. Now here, instead of bolting both sides, I'm only going to be bolting to the member, and I'm going to be welding the connected plate. Here for the gap, I'll just go ahead and do 1/2 inch. And for the dimensions, instead of center line, we can do top of steel. Double steel allows you to start from the top of the beam and extend your cleat as needed. So here for the offset, we'll leave it as 2 inches. I'll just edit this to 5/16 and start positioning the bolts onto the beam. So here for the beam, for the transfer edge distance, I'll do 1.5, and then I'll start spacing my bolts 3 inches. Now this technique is basically adding the spacing and however many bolts I want. So I want 4 additional bolts spaced at 3 inches. So now with this, I basically have a finalized model of my connection. Next thing that I want to do maybe is cut the flanges, the top and bottom flanges, and this is another good way that we can use the working plane. So with the working plane, we'll align it to the column. And here's where we can specify these cuts. So we'll start at the plate end, and then we'll choose the offset. Now, remember that we can use 2 different cuts. We have cut of member and cut of plate. In this case, since we only need the bottom and top flanges, we are going to use cut of plate. So for cut of plate, we'll choose the correct member. So column, bottom flange, and it's being cut by the working plane. As you can see here, the bottom flange is already being cut. All we need to do is copy and re-reference the modified item to be the top flange, and we are done. All right, for our fourth connection, we are looking at a 2-member base plate connection. If we start looking at this connection, you can see that member M1 has already been CJP welded onto the stiffening plate. All we need to do is add a new connection to member M2. To start it off, we'll look at the operations and click on a cleat operation. With this operation, we'll be able to add angle sections to connect member M2 onto the stiffening plate. So to start, for the members, I'll go ahead and choose member M2 Web 2. And to connect it, instead of the member, I will choose the stiffening plate 1. I'll go ahead and change my profile section. And for the location, I only want it on one side, so I'll choose the rear side. Now for the connection type, instead of bolted, I will choose welded. And I'll go ahead and remove the welding for the angle section onto the stiffening plate. Now here for the other parameters, I will remove the gap and adjust the cleat length for our connection. Now since I have this cleat on this side, I will also have to apply it onto the other side of member M2. To do this, instead of creating a whole new cleat operation, all I have to do is right-click, copy, and fix the different referencing members. So here, instead of Web 2, I will choose Web 4, and I'll adjust this parameter to be on the other side. All right, here's where we'll start looking at the bolt anchor grid operation. If we go to the operation, you will find it under the cleat operation, which is our 4th row, 4th option. We'll be able to add these anchors onto our connection. Now, first thing to learn about this is under the fasteners, you can change from bolts to anchors. In the item counts is very important because it defines how many plates these anchors are going through. So in our case, since we're connecting the angle section onto the stiffening plate, so we can add anchors that run onto a concrete block, we'll need 2 item counts. For our first item, the angle section is actually a member. So if we go under members, we can choose cleat 1, web 1. For the item 2, it will be SB1. Now for our fasteners, I will adjust the length to 12 inches and start positioning my anchors in the correct location. So here for the anchors, I will need to adjust the row, which will be, instead of 0 inches, I will do 1 inch. And for the position, I will choose 1.5 inch from the edge and the other bolt spaced at 3 inches. All right. Now for the foundation block, I will leave it as a new concrete block with the default parameters. If I do want to add anchors onto the other side for the other cleat, all I have to do is right click and copy. Now all I have to do is adjust these different parameters. And one of the very first parameters is adjust the member that we are referencing to. Instead of cleat 1, now we'll go ahead and choose cleat 2 and everything is fixed. But now these new anchors are being made on a new concrete block. So what we are looking at now are 2 different concrete blocks. To fix it, drop down menu and click existing block. Now these anchors are being placed within the same concrete block. Now we need to add the anchors that will be placed on the stiffening plate to the concrete block. And to start, I will add 2 rows of these anchors onto the stiffening plate. Again, all we have to do is right-click, copy, and adjust the item counts to 1. For the item, we are choosing stiffening plate, and now we just need to adjust the positioning of these different anchors. So for the rows, I do want it 11 inches from the center line onto both sides. To reference the center line from the positioning, all you have to do is add that semicolon in between. For the positioning, I will start at 52.5 inches. So I can start from the left and then add 6 more bolts or anchors spaced at 6 inches. Now for the foundation block, we are choosing an existing block so we can keep all these anchors within one concrete block. Now lastly, I do want to add a different pattern for my anchor bolt positioning, and this pattern will be to add 2 columns of anchors, one on this side and one on the left side of member M1. To do so, again, let's go ahead and right click for the grid operation, copy. Now for the item counts, we're still using one item, which is a stiffening plate. So all we need to do is adjust the position of these anchors. Now for the rows, I do want 3 anchors spaced at 5.5 inches in between. So I'll start with the first position will be at 5.5 inches. And then I want the other 2 anchors spaced at 5.5 inches. So I will do 5.5 inches, and I want 2 additional anchors. As you see here, the whole stiffening plate is being filled with these additional anchors because I haven't specified the correct positioning. Within this position, I am adding all these different anchors onto all those 7 anchor positions. So here I'll just do 2 anchor positions. The first one will be 16 inches and a half, and the other one will be spaced in another 18 inches. Doing so corrects the new position of these anchors. So not only are you able to fix these different patterns within your plate editor, exploding these anchors and then deleting which ones you don't need, but in this case where you might have to do a lot of manual work, all you have to do is add just different bolt anchor grid operations. With this, one other thing that we can look at is if we go to grid operation 4, within the type, here we will be able to add multiple anchor dimensions onto our model. For the case of this operation, or for the case of this connection, we will change this back onto the same anchors. So now that we have our connection modeled, all we have to do is click calculate. And I actually do want to run this model so that I can show you an additional piece of information for these steel to concrete connections. So if we click calculate, again, idea statica is iterating all these different loads until it's able to reach 100% of the analysis. Now, as the analysis finishes, we will be able to be greeted with a traffic light and a quick summary of our results, explaining all the different summaries for the extreme values of all the components, those components being the plates, anchors, welds, your concrete block. Now, as you see in these results, everything is passing except the anchors. What we do within the anchor checks is that we check for the concrete breakout resistance for both tension and shear. If we go ahead and observe our check results, specifically for anchors, we will be able to see that our anchors are failing due to these checks. If we go to our anchor checks so that we are able to see the detailed results for all different anchors, we will be able to see why these anchors are failing. So if we click on the plus icon, right click so that we can see all these different results a lot better, we will be able to see that our concrete breakout resistance is failing for these anchors. So now, let's say you did have a reinforced concrete for these connections. What IDEA does is we do provide these concrete checks, but these are for unreinforced concrete. If you did want to do your separate analysis for this, we do have a method for you to be able to turn off these checks. And these checks are found under the code setup. So we click on the code setup. Here for the concrete breakout resistance, we can actually choose what type of checks we want to perform, whether it be for tension, shear, or none. If we click none, click OK. All we have to do is rerun our calculation so that we can obtain the new results for these anchors without those given checks. All we have to do is click calculate and reanalyze our connection. Now with me, I already have a pre-solved connection with these checks already turned off. Now you'll see here that within the same given loads, our anchor checks are now passing these checks, because if we go under the code setup, we are not checking for either tension or shear for the concrete breakout resistance. Now this is one method if you do have reinforced concrete and you want to do that side check by yourself. You can always turn this off, and if we go to the check tab, we will be able to provide you this supplementary information so that you can do your checks on your own. So if we go to the plus icon for these anchor checks, right click print preview. At the end of all this information, we have this statement for the supplementary reinforcement, and that is that we provide you the forces for tension and shear for all these different anchors so you can perform your own check for the reinforcement. With this, you will be able to get a pass check for your anchors, and you will also be able to do your separate checks for the concrete breakout.